Okay, starting now for the next paper session. We'll be having 4 papers in this session, 10 minutes each. I'll just send a reminder at 8 minutes so that if you want to give any space for concluding remarks, you can time that accordingly. Let's start with the next paper. The topic is recipes for post-training quantization of deep neural networks. This is by Ashutosh Mishra, Christoffer Löffler, and Axel Plinge from Fraunhofer. Ashutosh, you can take over.
Sure. Just a second. Let me just share my screen. I hope everyone is able to see my screen, right?
Not yet. I think it will pop up soon. Yeah, feel free to switch on your video if you'd like to interact with audience as well.
Yeah, there seems to be some problem with my camera, so unfortunately I can't.
Well, your screen sharing works.
Okay, perfect. Okay, so hi everyone, myself Ashutosh from Fraunhofer IS Germany, and I together with my colleagues Christoffer and Axel have been working on analyzing quantization post-training on deep neural networks. And today, as part of this presentation, I'll be covering some of the work through our paper, Recipes for Post-Training Quantization of Deep Neural Networks. The motivation of which comes from the fact that as neural networks are becoming bigger and bigger, it is becoming more and more difficult to deploy on the hardware devices. And here, the potential research to solve this problem is huge. The advantages may range from like transmission size, if any, for federated learning, as one of the previous speakers talked about. It might also include energy to memory requirement savings, and also in terms of the inference speeds. And this field soon got momentum with a seminal paper from Zsolt, where he identified general categories for different methods to achieve compression of the neural networks. Which ranges from the first starts with the pruning, then followed by the lowering approximation, then quantization, and if there's any model transmission is involved, then probably entropy coding as well. But for this talk, I'll be presenting our results only for the quantization part. So in our paper, we explore quantization strategy from 3 different dimensions. First, based on the type, where we explore uniform quantization, and the other one is the adaptive quantization. On your screen, you see these 2 plots, which are the histogram of the weight values of a model. For the uniform quantization, it can be explained like you use a step size to map the high resolution values to low resolution values. So for the left plot, it would mean all these individual different colors. Different tensors marked with these different colors will be using their individual step sizes for the mapping from the high resolution to the low resolution. While for the adaptive case, it would mean that these different colors, the tensors with the different colors are being clustered using some clustering algorithm. For our work, we used k-means ++ algorithm. So these tensors will be clustered based on their proximity. And again, the resolution will still be the same. That will be 32-bit floating point, but the numbers will be limited. That is, the final network will be using just few representative 32-bit floating point values. Based on the clusterings that was resulted from the clustering algorithm used. The second criteria was based on the locality of the weight values. So for the global case, it would mean that the quantization parameter, that is a step size for the uniform quantization, and it would mean the code books resulting from the clustering algorithm for the adaptive case, they are based on the statistics of the weight values of the entire model. And that's why we are calling it as the global method. While for the tensor-wise method, we compute individual quantization parameters for the individual tensors. In the third scheme, we evaluate greedy-based approaches for assigning variable bits to different tensors of the model. We evaluate our improved version of a baseline greedy method, the details of which are in the next slide. So the greedy baseline approach that we use works like the one on the left side of your screen. We sort the tensors or the layers based on some criteria. For us, it was size. So we order the tensors in decreasing order of size. we have the start bits as the hyperparameter. We assign same bits to all the tensors of the model, perform the evaluation on the test set. Then we select the tensor with the maximum size and reduce its current bits and perform the evaluation again to check the accuracy drop. And if the accuracy drop is beyond a certain threshold, then we break the process for the current tensor, assign the previous best number of bits for this tensor, and move on to the next tensor in order. All the tensors are processed in the similar fashion until we get a good set of bits for the tensors. So we improve this straightforward approach by better initialization of start bits for the individual tensors, and we name it as T2. And the way it works is as follows. We add an optimization trick for the starting bits, which was motivated by our attempt to decrease the convergence speed of the baseline approach by greedy method. And and we assign the same, again, the algorithm works something like this. We assign same number of bits to all the tensors again, but this time we reduce bits for all the tensors and perform the evaluation. If the drop is within threshold, we continue reducing the bits, else we break the bit reduction step. At the end, we have a better initialization of start bits for the tensors of the model. And the rest of the pipeline is same as the baseline greedy method, which is named as TA. For a robust benchmarking of our methods, we choose models and datasets from diverse domains. For example, we use a VGG-like network for acoustic event classification, which is a audio tagging task from the 2018 edition of the DCase. Another domain that we choose was from image classification using the ImageNet 2012 dataset using a ResNet 18 network. Third one is a fully convolutional network for the hand tool activity recognition, where we use embedded sensors, including IMU, audio signals, and also magnetic information to classify the hand activities into 3 classes. And the last one is a encoder-decoder architecture-based very popular unit network for the MRI brain segmentation, which is nothing but a pixel-wise binary classification task. In our work, there are quite many hyperparameters, which I'll be going through now. So the first one is for the uniform quantization, we experiment around using bits ranging from 1 to 16, but for the adaptive, we use bits range from 1 to 8. And for the accuracy drop threshold ranges, we keep the same range for both uniform and adaptive quantizations, and which include from extreme to, low to very high values in order to cover the extreme cases as well. All these values are in percentages, so they would mean that we are experimenting around, how the quantization would affect. What kind of effect does the particular quantization bring in terms of the accuracy drop? How much can we tolerate? Whether we can tolerate up to 0.1% or 20%. So in order to cover the extreme cases as well. And for the pre-calibration step that we included in our proposed method, we use a value of our choice, which is 0.3. And this value is intentionally kept low because as a pre-calibration step, we don't want to be too much forgiving, and we just want a nice set of start bits, and the rest of the work will be taken care of by the regular greedy approach from the which we named as TA.
2 minutes.
Okay. So now talking about the results on your screen, you see now the results for the uniform quantization case. On the x-axis, you see the relative compression size, and on the y-axis, you see the relative accuracy. So summarizing the results for the uniform quantization, the tensor-wise approach where we are using, individual quantization parameters for individual tensors that performs better than the global. The tensor-wise is being shown by this green color, and the global approach is being shown by the red color. Consistently, the global approach is being outperformed by the tensor-wise approach. The baseline greedy approach is of no help here, which is being shown by these blue circles. However, our approach is almost as good as the tensor-wise approach. And the similar pattern is being shown between the tensor-wise versus global in the adaptive case as well, which is now displaying on your screen. However, the adaptive case holistically is better than the uniform, but the benefits of variable bits is much more profound for the adaptive case, as both the greedy approaches consistently outperform the tensor-wise method, which was not the case with the uniform method. Also, our proposed approach performs similar or better compared to the baseline approach. However, for the FCN, you might see that the global quantization method is not performing at all, and the reason being that there was a weight collapse of one tensor, which resulted into the underperformance of the global method. With these results, we show the competitiveness of our approach versus the other methods, but the real advantage of our method is showcased in terms of the optimization steps needed to converge. A simple pre-calibration step for a better start bit initialization vastly reduces the huge search space and hence converges faster, as is shown in these plots on your screen. On the left side, you see the results for the uniform quantization case, and on the right side for the adaptive quantization case. You can see our proposed method consistently outperforms the baseline greedy approach in terms of the evaluation steps or the optimization steps needed in order to reach the final result. For the adaptive case, we are showing the result averaged over the 5 runs. To end this presentation, summarizing our work, overall adaptive quantization performs better than the uniform, but with a small overhead of lookup operation using the codebook during the inference. Using local quantization based on tensor-wise statistics is better than global quantization. And lastly, the best results are achieved, however, through variable bit assignment using greedy method, where our proposed method performs similar or better than the baseline method, but outperforms all the methods in terms of the optimization steps needed to converge. And with this, I would like to end my talk, and thanks for listening.
Thank you, Ashutosh. That was right on time. Yeah, in lieu of time, I'll be moving on to the next author. This is about FactorizeNet, progressive depth factorization for efficient CNN architecture exploration under quantization constraints. This is presented by Stone Yun and Alexander Wong from University of Waterloo, Canada. Stone, Yun, if you can take over and start presenting.
Hi, yeah. Is my screen share showing yet?
I think it's popping up in a sec.
Okay. Just give that some time.
It's black.
It's still black? Oh, okay. I'll try one more time. I've been having some issues with Teams screen share sometimes, so how about now?
Yeah, I see it.
Okay, perfect. I guess second time's the charm. So it's this slide showing up in full screen yet?
It's not on full screen though. I think it's.
Is it working?
It's showing, yeah.
Okay, cool, great. Hi everyone, my name is Stone. I'm a student at University of Waterloo, supervised by Alexander Wong, who spoke earlier today. So the work I did was kind of looking at how progressive depth factorization might be a tool for searching for efficient CNN architectures, and then also exploring this behavior under quantization constraints. So for in TinyML settings, we've all had a common design process where you might start with a state-of-the-art architecture that's rather large, and you verified you can get some good results, and you're ready to start adapting this to actually fit on your mobile chip. And so for mobile inference, depth factorization, such as in depth-wise separable convolution and uniform quantization, have quickly emerged as top tools for enabling this mobile inference. You know, a lot of the accelerators such as DSP, they're already optimized for massively parallel fixed point arithmetic. And so deploying CNNs to a uniform quantization setting, it makes for a very smooth transition. However, mobile nets and depth-wise separable convolution are really just one part on the extreme end of this spectrum of factorization that you can perform on your convolutions. We know in like ResNext or ShuffleNet, you have various group convolution settings. And so as mentioned by Francois Cholet in the exception paper, we shouldn't necessarily assume that the fully depth-wise convolution is always the optimal choice for a given application, because in that setting where you've completely decoupled the channel-wise correlations, it's not necessarily going to be the best setting all the time. And so besides searching for these optimal depth-wise factorization settings, I also wanted to see if I could find a way to get a better understanding of how these different architectural design choices might affect the final quantized behavior. Oftentimes with our prototyping and experiments, we're going to make design choices based on the floating point behavior, and we don't really know how the quantized behavior might turn out until later. So we're kind of seeing this shift in mobile machine learning designs where we're all now being much more aware of the effect of quantization on our neural networks. And so in our method, we wanted to perform this systematic, stepwise process of exploring this what I call quantization space. So when you have your regular CNN or other kind of macro architecture, and you're ready to start making it more efficient and reduce its memory and computation footprint for the mobile chip. And so what you could do is you progressively increase that rate of factorization of each layer in your network. And so with every layer and increasingly deep networks, you end up having this combinatoric search space of various depth factorization configurations. And so we performed we started with an initial CNN, and then we progressively increased this rate of factorization for each layers. And at each step of factorization, we have this new candidate architecture. And then we wanted to perform some fine-grained analysis of the architecture in hopes that it can give us some more insight on the behavior. And so with this proposed method, besides enabling the finding an optimal depth factorized architecture, we can also see kind of these trade-offs between efficiency and accuracy. And so to start with my initial experiments, I played with two more manual factorization settings. I called them uniform and reverse pyramid. The uniform factorization is like a naive setting. Basically, I just assigned a single factorization rate to all of the layers in the network. And then with a more intelligent method, which I called reverse pyramid, basically every time the input depth to a layer doubled, I would also double the factorization rate. And so with my reverse pyramid factorizations, I defined them with the initial factorization rate at the beginning of the network. And so with this, when you double the factorization rate every time input depth doubles, then effectively with these groups of convolutions, every group will have the same number of channels regardless of where you are in the network. So when you increase the rate of factorization to be equal to the number of input channels, you effectively get depth-wise convolution that we see in a lot of efficient neural network architectures today. And so using this iterative method, we could isolate the changes in behavior to be due to these changes in factorization of every layer. And then by using a fine-grained analysis, we wanted to get a more detailed picture of how the different stages and layers will respond to these progressively increasing factorization settings. And so for that analysis, it was basically just we were trying to analyze the distributions of weights and activations at each layer, so we can try and build a picture of how information is passing from layer to layer, as well as how these distributions might interact with quantization noise when we've converted to like 8-bit fixed point. There's a previous paper I read where they used the layer-wise signal quantization noise ratio to look at how they could improve the MobileNet's V1 architecture. And then based on that analysis, they retrained it and were able to recover a lot of accuracy. And so kind of building on that, I went to an even lower level and was trying to use various statistics to analyze these distributions of weights and activations. So another thing worth noting is that besides looking at just the weights and activations, all the CNNs for mobile inference often have batch norm, And in order to enable fast inference, we need to fold those batch norm parameters into the parameters of the previous convolution layer. And so since it's these batch norm folded weights that are actually being quantized, we need to also analyze how the distributions of the batch norm folded weights might change. Also wanted to highlight that the precision quantity was really just a ratio of the channels range compared to the range of the entire tensor. And it's kind of like a proxy measure for how representative the tensor's quantization encodings will be for the information in that individual channel. So if the range of that one channel happens to be much smaller, then we could imagine that the quantization noise that gets introduced might be large enough to like overwhelm that information. So I trained, the initial experiment was a fairly small set of architectures. It was mainly just 7 architectures. I have there's the regular convolution, that starting network that we had, and then as the factorization rate increases, we start to see this trade-off of accuracy and max. And then on the far end is the fully depth-wise separable convolution neural network. And so we kind of see like there may be certain architectures that will have very similar accuracy, both floating point and quantized, but they have a very different number of total computations required for a single inference. And so we could see this this brown cross, which was the reverse pyramid factorization with an initial rate of 2. It can achieve over 2 times reduction in max compared to our initial starting architecture, and it could be a fairly small reduction in accuracy. So another thing that stood out in this first search was the drastic drop in quantized accuracy when I quantized FactorizeNet F16, which is uniform factorization, and the factorization rate was 16 for all the layers. And so I wanted to, we were seeing if maybe our fine-grained analysis could yield some information on that. Just kind of looking at the batch norm folded weights, the activations, and the precision of the batch norm folded weights, I'd see that the batch norm folded weights ranges were generally larger for FactorizeNet F16 compared to F2, as well as the activation ranges being larger. And then the precisions at the same time were smaller. And so it kind of appeared that there was more sensitivity to quantization in these early layers where information may be lost. With the depth-wise separable convolution quantized actually unexpectedly well in this experiment. We've seen in the literature there's well-documented issues with just regular post-training quantization for mobile nets. And so that's something I'd like to further investigate. In some of my follow-up experiments after, there was quite a bit of variability in the quantized performance. And so I think I need to have a better understanding of this variation in the performances that we observe, because that can change based on the data set you use for the calibration or the training, how the training dynamics actually play out. And so for future work, we want to explore use of more intelligent search algorithms, hopefully some automated architecture search algorithms to search through these different factorization settings, as well as analyzing how the sparsity of activations will change at each layer, because that can give us some insight on the features that are being extracted, and then as well as exploring how we can use depth factorization to condense more complex CNN architectures such as ResNet 152. So thank you for listening.
Thank you, Qian. That was perfect on timing and excellent work. It was nice to know about this.
Thank you.
Again, in lieu of time, I would just be moving on to the next talk. So I would ask everyone to hold their questions until the next break that we are having. Thanks for accommodating.
Thanks. Okay, thanks.
Yeah. The next talk is on auto-Hessian aware channel-wise quantization of neural networks. It's by Sushan, Victor Lee, and Cruz Darren from Intel. Shan, if you can start the presentation, that would be great.
Yeah. Can you hear me?
Yes, and we can see it. Yeah, thank you.
Yeah, so you can see my sharing, right?
Yes.
Okay, so I will get started. Hi everyone, my name is Qian, and I am working at Intel as a machine learning engineer. Currently, we are focusing on model compression techniques. Our paper is called AHCQ Auto-Hessian-Aware Channel-Wise Quantization of Neural Networks. And there are 3 authors of this paper, me and Victor Lee and Darren. And this is the agenda of my presentation. First, I will introduce mixed precision quantization, and then I will show you the power of Hessian traces in quantization. After that, I will go through the details of my invention, and the last is the experiment results. First, about mixed precision quantization. Currently, the most widely used quantization method is uniform quantization. And in uniform quantization, we set all the layers of a network to the same bit. However, different layers of a network may have different sensitivities, so it is reasonable to use different bits for different layers, as the figure on the upper here shows. And obviously, using mixed precision would increase the accuracy at the same compression ratio compared with uniform quantization. However, the search space is too huge for manual setting every layer with different bits. So in a recent paper, HAWQV2, the author proposes to use Hessian trace to solve mixed precision problem. Hessian matrix or Hessian is a squared matrix of the second-order partial derivative of the weights or activations, and Hessian trace is the trace of the Hessian matrix. As the figure on the bottom here shows, the author calculated the Hessian traces of different layers of ResNet 50. As we can see, the gap of Hessian traces of different layers is very huge. After adding perturbation to the first layer with a very high trace, the loss changes rapidly as the perturbation increases. And for the 52th layer with a very low trace, the loss landscape is relatively flat. And this experiment shows that Hessian traces are great indicators of the layer sensitivity to quantization error. And in our paper, based on the insights of HAWQV2, we extend the Hessian trace experiment to channel-wise manner. As the lower left figure shows, we plotted the sorted average Hessian trace of different channels of ResNet 18 in descending order. And as the right figure shows, the loss changed rapidly if we add perturbation to the channel with the maximum trace, and the loss stayed relatively flat when adding perturbation to the channel with the minimum trace. And this experiment shows that Hessian traces can also serve as the indicator of the channel sensitivity to quantization. And in channel-wise quantization, every channel may have a different bit, so it is clearly more fine-grained than layer-wise quantization, and so it's more promising to achieve a better performance and better accuracy. But the search space increased hugely for channel-wise bit allocation. For example, in ResNet 50, there are only 54 layers, but there are over 27,000 channels. So the bit allocation method proposed in HAWQV2 won't work for channel-wise quantization. To address this issue, we proposed a reinforcement learning-based method. First, we sort the Hessian traces of different channels in descending order, as the lower left image shows. We have demonstrated that Hessian traces can serve as the indicator of the channel sensitivity to quantization in the last slide. In other words, channels with higher traces should be assigned with higher bits. So the channel-wise bit allocation problem can be reduced to an integer partition problem with the help of Hessian traces. The only parameters missing are the fractions of channels to be quantized to different quantization bits. In our paper, we propose to use the actor-critic model with DDPG agent to give the action the fractions of channels to be quantized to different quantization bits. As the figure on the lower right shows, we first use the agent to generate the fractions of a certain quantization bit, and then we quantize the fractions of channels to that certain bit according to the sorted average Hessian trace. And finally, we fine-tune the quantized model and get the accuracy as reward to update the agent parameters. This process goes on until the agent converges. After the agent converges, we use the optimal parameters to retrain the model and get the final accuracy. And this is the experiment results of our paper. Compare with state-of-the-art mixed precision methods like HAQ, AutoQ, and HAWQV2, we can achieve about 1% higher accuracy top one at the same compression ratio. Also, as the right figure shows, our agent training efficiency is much better than traditional reinforcement learning-based methods like HAQ and AutoQ, because we have a much smaller action space. And that is all for my presentation. Thank you all.
Thank you. That was great. We actually have a couple minutes for Q&A if anyone has a quick question, or we can move to next one. Okay, I guess everyone's holding their questions for the break sessions. We look forward to it. Yeah, I encourage all authors to hang back until then. So if anyone has any question, they can reach out to you. Thank you for this. We'll move on to the next. This one's on hardware-aware sparsity generation for convolutional neural networks. This is by Xiaofan, Zsolt, Biro, and Cormac from Intel. So if you can start the presentation, that would be great. I think you're on mute.
Can you see my screen now? Hello?
Yeah, we can hear you.
Okay. Is it showing up now or?
Yeah, we see it.
Yeah, we can see it.
Okay. Okay, so the topic of my talk is hardware-aware sparsity generation for convolutional neural network. The reason for doing this work is because nowadays there are more and more hardware that are starting to support sparsity accelerations for the networks to run on these networks. So that's gave us the motivation to start the work. So before I talk about the hardware-aware method, I will start to talk about the general reinforcement learning using in sparsity. So once you have a baseline model, usually they are fully densed, and then you pass into agent training, which is the reinforcement learning training. And in our case, the agent we are using is the DDPG agent, which is Deep Deterministic Policy Gradient. For the agent, it will generate an action for a layer and for a particular layer, and then pass into the environment, which is weight pruning in our case. And after it's generating a sparsity level, it will have an embedding. The embedding is like a signature of that particular layer. So the action is generated for each layer in the network, and it passed through all the networks, and then finally it will generating a reward. And the reward in our case is the accuracy. So this pipeline will go through with few hundred iterations in order to get a best reward sparse model. And that best reward sparse model will go through a fine-tuning stage. And this fine-tuning stage is optional based on your target target accuracy. So after this fine-tuning stage, then you will have a final sparse model. So this is a general overview of sparsity generation using reinforcement learning. So for our work, we including the hardware-aware components into this pipeline. And the agent is the same agent, DDPG. And for the action, it will give a sparsity level for this particular layer. After it's generating the sparsity level, it passes into a simulator. So this simulator simulates the hardware behavior of that sparse layer on that particular hardware, and it output a number of cycles that required for that sparse layer to run on that particular hardware. So after all these layers are generated with sparsity and number of cycles, the cycles is embed into the embedding. And then it will output a reward, which is the accuracy, then pass back to the agent, like the non-hardware aware method. So difference for our work is the embedding state. So for the embedding state, it has the T, which is the layer index, and NCHW, which is the input channel, output channel. HW is the input feature map, height and width, and stride for the weights and kernel for the weights. So weight T is the number of parameters left in that layer. And cycles T is the number of cycles it generated from the simulator for that sparse layer. And reduced is the number of reduced cycles for the previous layer, which is sparse layers. And the rest is the rest of cycles that require for the rest of the layers. And AT-1 is the action we took for the previous sparse layer. So the action we used for our work is between 0 and 1, and it's a continuous space. So the reason for using a continuous space action is because it gives more searching space and it also reduces the accuracy loss. But we also gives a limitation for our action. So by setting the number of cycles that target cycles that we want for this particular network to reach. So which means, so if the previous layer, after it's generating the sparsity and calculating the cycles, if the number of cycles did not reach our target level, so for the rest of the layers, it will prune aggressively in order for us to achieve that target cycles. So for the fine-tuning stage, as I said before, it's optional. But for all our work and all the experiments we took in the work, it required only like 1/10 of the epochs of the original baseline training epochs. So which means for original training for ResNet or mobile nets, it's about 120 epochs. And for our fine-tuning stage, it's only about 10 to 30 epochs max. So. And here are some results. So the top table is the hardware aware method, and then the bottom table is the non-hardware aware method. So for showing this is for comparison. And then there are more results on the paper that you can have a read. So here is only ResNet 50. So for the target aware, hardware aware method, we set a target of 45% of the target cycles. Here you can see like 45%, of the original cycles. And with 45% of original cycles, we reach like less than 1% top one accuracy drop, but with only 65% of sparsity. And for the non-hardware aware method, as you can see, the target is different. So it's generating sparsity only and without the hardware information. And you can see with 70% of sparsity, it requires 61% of the original cycles, which is way more than the hardware aware method. And which means if you have a higher percentage of sparsity, doesn't mean you will run better on a particular hardware. So there are more results here. The reason for showing this is I want to show the MobileNet V2. So MobileNet V2 is already a very efficient network because it's designed for embedded devices. So if people knows about this network, we all know it's quite hard to prune or generating sparsity. So for the hardware aware method, you can see that we can reach which is much less number of cycles than the non-hardware aware method, and within only 1% top one accuracy drop compared to the non-hardware aware method. And you can see all these from the ResNet 18 and ResNet 50, which means the hardware aware method include the hardware component into it. It's an essential part. But as you may argue, like there's a slightly accuracy drop between the hardware-aware method and non-hardware-aware method. It's because so different hardware perform differently with sparsity levels. And our hardware-aware method can simulate these hardware behavior. And on this particular hardware, for the activation, it also like look into the activation sparsity. So once the activation sparsity reach a certain point, a certain sparsity, and no matter how much you prune for the weights, you can't really see much gain. You can see that with a ResNet 50 example in this case. So this activation sparsity distribution was generated based on a batch of images. And you can see for the later layers, you have much more sparsity for the activation. And then the hardware-aware method can simulate this behavior, so it prune much less in the later layers, and it prune much more in the earlier layers. But the non-hardware-aware method did not know the hardware behavior, so it prune much more in the later layers. So we all know that the earlier layers is more important accuracy-wise. So that's why it can generating a slightly higher accuracy than the hardware-aware method. But overall, our hardware-aware method can give or like less than 1% accuracy drop and much better behavior on a particular hardware. So that's all for my talk.
That's amazing.
Thanks.
Yeah, I think you're right on time.